Okay, welcome back. Now, before we start with the part about the molecules, I'd like to briefly show this paper that I would have liked to show you before. Can you show the presentation? Okay, yeah, so this is this experiment where this terminology of photoelectron holography was introduced, and they see here really an unprecedented number of these holographic. Oh. Of these holographic interference fringes, and this was an unusual scenario in which this measurement was conducted. Namely, they used a free electron laser. This is the paper title. They used a free electron laser operating at 7 micrometer wavelength, and because the intensity of that laser was quite small, they used excited xenon atoms that were prepared in a special kind of atomic trap. Yeah, and then they looked at photoelectrons from these excited atoms. Yeah, and then they got these beautiful images. Okay, now back to molecules. This is not what I wanted. There we go. Yeah. Just a second. I want to close this there. Okay, anyway, that's not important. Okay, so yeah. So this is the overview from the script. What you see here is so we will look at parts of this. So for the first part, I will give an overview and hopefully discuss the most important parts. And then for the second part on rotational dynamics, due to time restrictions, we can only look at the highlights. But I hope it's still interesting. Okay, laser physicists here. We have our pioneer Arthur Shallow. They seem to have a mixed relationship towards molecular physics. So Arthur Shallow famously said, a diatomic molecule is a molecule with one atom too many. And I would say we have to disagree quite strongly because, not molecular optics, in a way, have received the Nobel Prize for Chemistry in 1999. Yeah, so this is Ahmed Savail. He's well known as the father of femtochemistry. So his work does not necessarily involve intense laser fields. However, it involves femtosecond laser fields, and those are usually quite intense simply because you confine a certain amount of energy into an extremely limited amount of time. So you end up with a high intensity. And so what he especially did was that he probed transition states in chemical reactions. So when a chemical reaction takes place, the molecule is in intermediate states in between, and he was the first one to discover these states and learn quite a bit about them using femtosecond techniques that were all based on lasers. And because lasers are the only source to make such short events. And so why should we study molecules apart from the fact that it has given a Nobel Prize before? I'm missing the first. Anyway, So, well, most gases in our world are molecules, and reactions of atoms itself are rather boring. So that's therefore looking at molecules rather than just atoms is the natural extension of what we discussed so far. Furthermore, we actually have the potential with intense lasers to study isolated molecules and how they interact with light. And so we can look at chemical reactions in on the single molecule level. So there's also much fundamental interest. And one of the things that make molecules so interesting is that they can not only undergo electronic dynamics, but also the nuclei can rearrange and move inside the molecules. And this motion, of course, gives rise to chemical reactions. We will get to that. Let's first go to the iPad. And I'm really missing some of my notes. Okay. Did I? Yeah. So now I mentioned that that molecules are well, that they can undergo so many dynamics, and what's this one, that would be nice, because otherwise I lose track. Okay, see, I would have forgotten this part about it, namely, so what's different if we now consider a molecule rather than an atom? Yeah, so in an atom, the picture that we like to draw was this here. Yeah, so we have here space, x, and then we plot here the energy, and now we have our atomic potential, and we add to it a laser field that has a potential like this one. And then the resulting potential would look something like this. Yeah, and we have here our ground state and a tunnel through which the electron can tunnel. Now let's draw the same for a molecule in one dimension. Yeah, so a diatomic molecule. Now we have not just one nucleus as here, but we have two of them. And so in the field-free case, the potential between looks something like this. This one a bit lower. Yeah, here. Here the field-free potential would be simply 1 over r. And in this case, so this would be atom. We have two of such potentials, but they are offset a little bit. Yeah, we typically call the distance between the nuclei, we typically call capital R for the internuclear distance. So this one would be at r over 2, and this one would be at minus r over 2. So now if we want to write down a value for an expression for this potential, we have r plus r over 2 plus 1 over, actually needs the minus sign, of course, minus r over 2. And then these are absolute values. Yeah? And now if we add a laser field to it, then out here, this looks this looks more or less the same. But now, of course, as we mentioned in the break briefly, this electron would be electrons localized here would be much more likely to tunnel. We should note that we have electrons that are close to the core, and these are, of course, always not very likely to tunnel. But we also have valence electrons that are delocalized. And now, when we stretch, the molecule, so we increase R, what will happen is that this barrier, the height of this barrier will increase. Because you move this one out, you move that one out, so this goes closer to the 0 level. And at infinite distance, there would just be separated atoms. But as you increase the internuclear distance, this will go up. So eventually, these delocalized valence electrons, they may localize on one of the atoms. And then, of course, the molecular bond breaks. And a similar and this localization here of the electron, or the delocalization, this of course determines the molecular behavior. And now, as you change the orientation or the alignment of the molecule with respect to the laser field, so the molecule can be aligned like this or aligned like that. This will certainly also make a difference, because in the one-dimensional representation, the nuclei here would be much closer than in this case. So we can expect that the shape of the molecule, as well as the alignment with respect to the laser field, is important. And we will even see that all these dynamics can be intertwined, and this gives the possibility to manipulate the dynamics of the molecules and even chemical reactions. Okay. Now, how do we treat a molecule in the most general case? The key to that is, an important key to that is the Born-Oppenheimer approximation. Let's motivate this and discuss what it means. So 911 is the Born-Oppenheimer. Okay, I should spell it out. Okay, so let's assume we have a molecule consisting of a certain number of nuclei K and a certain number of electrons, capital N. Molecule with K nuclei and N. Well, these are only the valence electrons, yes? So we assume that core electrons do not take part in the molecular dynamics. And then we can write the Hamiltonian in the field-free case, so there's no external laser field yet, as the following. So of course we have kinetic and potential energy, and all these particles are charged. So let's begin with the kinetic energy. We have n electrons. So we sum over all the electrons, and each one has a certain momentum. And and that relates to this kinetic energy. So this is the kinetic energy of the electrons. We have a similar term for the nuclei. Pk squared over the mass of the nuclei, which can be different, of course. Kinetic energy of nuclei. And now the electrons and nuclei can also interact. Yeah, so this was now the potential term. So the most complex one is, of course, the interaction of electrons and nuclei. So we have to sum over, we have a double sum where we sum over all electrons and all nuclei. And this is the charge of the nucleus. And now this is these are the position vectors of the electrons and the nuclei. And so this would be the electron-nuclei attraction. Then we have the attraction between nuclei. I see there's a mistake in the script that came from using copy and paste too much. Yeah, so this would be the electron-electron interaction. And then we have, and this is of course a repulsion. Yeah, so this is the electron-nuclear attraction. And now we have to do the K larger than L. Zk, Zl. These are the charges. Rk minus Rl. Yeah, so this would be, so if you can solve the Schrödinger equation with this Hamiltonian, then you can, well, then you can solve any molecular dynamics. So if we can solve this, we don't need chemistry anymore because we understand all of it. Okay, but of course this is insanely complicated. Yeah, so for H2 plus, yeah, so that's the simplest molecule. We have 2 protons and 1 electron. Then you can actually do this. Yeah, then you can do it. But once you have 2 electrons and 2 nuclei, H2, then it's already beyond the capabilities of computers nowadays. And yeah, so a more complex molecule such as CO2 or, well, proteins, of course, that's you don't even have to try. So the idea of that we now have to simplify this was brought forward by Born and Oppenheimer, and it relies on the fact that electrons are much lighter than nuclei, and therefore they move so fast that whatever the nuclei do, the electrons can simply follow. And this allows us to simplify this problem greatly. And so idea, electrons are much lighter than nuclei. Yeah, so even in the case of protons, it's a factor of 2,000 almost. So they can instantaneously follow the nuclear motion. And even in the case of external forces, they will be the first ones to interact. Yeah, so imagine you have this molecule consisting of nuclei and an electron cloud. You apply an external electric field, then the electrons will follow the field as the first, and only then the nuclei will slowly start moving. If you have a quickly oscillating field, then the nuclei are essentially just frozen and the electrons may wiggle around. Yeah. Yeah. In yeah, electrons will react first to external forces on a longer time scale. The nuclei react to the change in electron density. Okay, and there's a nice, can you show the laptop? There's a nice absorption spectrum here of water that illustrates this effect. Yeah? Of course, the time scale of the motion is related to the energy associated with transitions that correspond to either electronic or nuclei dynamics. Yeah? So this is the absorption spectrum of water. We have here in the visible range, there's essentially no absorption taking place. Yes? This is why water appears transparent. If we go to higher photon energy towards the UV, then the light will interact with the electrons. And this gives rise here to this very strong absorption. If you go to longer wavelength, on the other hand, yeah, so this is now related to the greenhouse effect in the atmosphere. Water is well, actually the strongest greenhouse gas, and it will here actually the nuclei will respond to the infrared light. Yeah, so the infrared light is not does not carry enough energy to promote electrons to higher electronic states, but as we discussed, it will induce a dipole, it will induce a change in the electron density, and then the nuclei will respond to that change. I mean, this is one way to see it. Yeah, and even here we can actually split into vibrational motion and rotational motion. In the case of rotational motion, the molecular structure is not directly changed, but the molecule simply rotates. And these are very low, associated with very low energy. Yeah, and so this shows that really the electronic time scale is roughly 1,000 to 1,000,000 times shorter than the nuclear time scale. And well, now, yeah, let's go back to the iPad. A second. So this separation of the electronic and the nuclear dynamics, this gives leads us to basically a recipe how we can solve the problem of the how we can solve the Schrödinger equation for molecules. Because first, so mathematically, by the way, this means that we can separate the wave function into an electronic wave function and a nuclear wave function. And now in the first step, we will solve the electronic problem. Yeah, because we'll just pretend we're now working on the attosecond to femtosecond time scale, and here the nuclei are just frozen, and then we solve the electronic problem for frozen nuclei. First, solve electronic Schrödinger equation. So that's the time independent because we're interested in the electronic states now. And here we'll assume that the nuclei are frozen. Yeah, so they're basically parameters. Yeah, so in particular, if you think of H2 plus, where we have just one electron, this is a relatively simple task to do. Yeah? First solve electronic equation where Rk equals constant. And so if you do this, I mean this is essentially the eigenvalue problem for the Hamilton operator. And so what you get are the eigenfunctions and the eigenvalues. The eigenvalues are these energy values here for this particular set of internuclear distances. Obtain eigenfunction and eigenvalues. So this is we call these EE. Oops. Yeah. So to be clear, what they would look like. So the eigenvalue is, of course, simply a number. Yeah? This would be the eigenenergy for a certain nuclear configuration. And then the eigenfunction is the electronic wave function, typically in 3 spatial dimensions. But as a function of the parameters, I mean 3 spatial dimensions for each electron. Yeah? So there's also, if you just have one electron, it's not too complicated. But if you have many, it's still complicated. And now the next step is to repeat this for different RK values. Repeat for different RK. Yeah, so in our simple example of H2+, there's a diatomic only has 1 internuclear distance, of course. So it's just one parameter that we vary. And now what we obtain is the electronic wave function. Yeah, so essentially the electron distribution, the electron density distribution around the nuclei, and the eigenvalues. And now we have obtained the eigenvalues as a function of the internuclear distance. So that's a curve. Yeah, so so this would be 5. This now would be 6. Interpretation. E of RK represents an energy curve. Yeah? So an energy as a function of the internuclear distance. And we can interpret this as the potential energy curve on which the nuclei move. The potential energy, well, in the one-dimensional case, it's just a curve. In a 2-dimensional case, we would actually obtain, we would obtain k times k minus 1 over 2 dimensional hypersurfaces. Yeah, so these are k times k minus 1 over 2 dimensional hypersurfaces. Yeah? So the simple example is k equals 2. Then we have 2 times 1. That's 2 divided by 2. That's 1. So it's just a curve, one-dimensional. In the case of, I move this down here. In the case of 3 atoms, yeah, so 1 dimension. Yeah, so here we have just 1 internuclear distance, so it's 1-dimensional. Sorry, I should say 2 nuclei. K equals 2. In the case of k equals 3, in the general case we have some sort of triangle in which the nuclei are, so we have 3 internuclear distances. So this should be 3-dimensional. So let's do the math. 3 times 2 is 6, divided by 2 is 3, and then so on. So this seems to make sense. And yeah, so back to our next point 6, these energy curves or energy hypersurfaces, they represent the potential energy surfaces or hypersurfaces on which the nuclei move. Yeah, can you show the presentation? Yeah, so this is what this would look like. Yeah, so this is now for H2 plus. We have here two electronic states. Yeah, these are the name of the states. They're not so important why they're called like this. Yeah, so again, how did we get here? We fix the nuclei at a certain distance. Yeah, so for example, here 1 atomic units, and then we solve the electronic problem. Then we did the same for maybe 1.1 or so, and at each, and then so on until 8, and each time we got actually here 2 eigenvalues. And then we plot them. These are the curves that we obtain. And in addition to that, we also get the electronic density. And these are displayed up here. Yeah, these and these. And actually, as it turns out, there's a binding molecular orbital, this one here. And there's an anti-binding one. Why is this an anti-bonding one? It has, there's no electron density right in between the nuclei. So in a way, since there is only one electron in here, you can classically think of this as being two protons with half a partial charge each. And then, of course, they will repel each other. In that case, however, there's actually the highest electron density is between the nuclei, and so the electron serves like a glue, if you want, to hold together these guys. Yeah. Okay. So we have here one binding curve and one not binding curve, and now comes the second step, which is now to calculate the states of the nuclei, which means you solve the time-independent Schrödinger equation for the nuclei, and you obtain these vibrational states. Yeah, so this would just be taking into account this motion. And whereas this one here would have discrete states, the anti-binding potential would not have any bound states. And then, of course, you can think of making a transition here, but we'll get to that. Before that, we discussed this here briefly. Now you can also take into account the rotational motion. Yeah, there's a Hamiltonian associated with it, and this gives rise to these to these curves here. These are the rotational states, and each vibrational state has many rotational states. However, these you can actually think of very high J numbers here, and then the energy value of the rotational states can well be comparable to these vibrational states, and in the most extreme case, even comparable to the electronic energies. And when something like this happens, the Born-Oppenheimer approximation fails. Yeah, because then you no longer have the separation of time and energy scales. Okay, I have to speed up a little bit. Okay, yeah, thank you. Okay, so what we'll do now is we'll consider the action of an external electric field, and now we of course have this intuition that when we absorb a photon, that let's say you have a photon of the size of this arrow, then you can make a transition from this point to that point. Whereas if maybe you're here Yeah? So maybe your molecule is at the internuclear distance of 5 atomic units, then that photon would not be in resonance anymore, and you would need a smaller photon. Yeah? So we want to see a bit how we can reconcile this picture with, this intuition with this picture here. How does this work? And the key to that is the dipole that's induced by an oscillating electric field in the molecule. Yeah, can you go back to the iPad, please? So we'll assume a two-level system in an E field. And so point 2, an external E field will induce a dipole dE by displacing the electrons. Yeah? While the nuclei are still assumed to be frozen. And then we have, and via this dipole, the molecule interacts with the laser field. And so this gives rise to the following Hamiltonian. And of course, now we need the time-dependent Schrödinger equation because we apply a time-dependent electric field, and then we can write the Hamiltonian as the field-free Hamiltonian plus this dipole interaction. Yeah, this, which is simply the scalar product of the dipole times the external electric field. Yeah, or the time-dependent Schrödinger equation could be written like this: I h bar d over dt is the field free, and then the dipole interaction. Yeah, and this is actually the nuclei. This is the nuclear wave function. Okay, and we assume that we have a two-level system as we saw it for H2+. So we can actually have two wave functions, one on each of the electronic states. Yeah, so with phi equals C1 times phi 1 plus C2 times phi 2. And these factors here, these are complex numbers, and they describe the population in each of the two electronic states that we consider. And now it can be shown, I don't have time to go through this, that the Hamiltonian can be written in the following way. It can be shown. So you will find this in the script. And I will actually make the extended version of the video available on YouTube, which I recorded last year for the lecture. Yeah, so this is a compact notation. Yeah, and you have here on the off diagonal, you have this dipole interaction. C1, psi1, C2. Phi 1, phi 2. Yeah, and now if you consider that E times D, that the electric field is 0, then you simply get then for Yeah. I guess I should better write this as phi 1, phi 2. So this, of course, the time derivative. Yeah. So if you assume that the electric field is 0, then you simply get 2 separated differential equations. Yeah, because then you get phi 1 dot equals E1 times C1 phi 1. So there's no time dependence, because this is just the eigenvalue. However, if this is not 0, then you get cross terms. And now, so I should have what? Yeah, you're right. Thank you. Those factors are missing, yes. C1, phi 1, C2, phi 2. And it's and actually these from this we also get the time dependence of these the time dependence of these factors. Yes. So it's better to put the d over dt here. Yeah. Thank you. And this is actually the reason why I wrote phi dot, because phi because that contains these factors. Yeah. Okay. Now, when you read the literature or hear scientific talks, people often say the laser field couples these states. Yeah, I always found that it's a bit of a strange expression. What's really meant by this is that the laser field, which enters here on these off-diagonal elements of the matrix, is responsible for coupling these 2 differential equations. Yeah, so as we just discussed, if the electric field were 0, then these were 2 uncoupled differential equations. But by having a non-zero field, the equations are coupled. And this is why they say this leads to coupling of these states. Now, as you notice, there's no photons in this picture. Yeah, so this generally means any electric field can couple. Yes, an electric field of any frequency can couple 2 states of any energy difference. Yeah? However, the efficiency is much different. And indeed, when the energy difference of these states corresponds, this energy difference corresponds to the frequency of the field, then the coupling is most efficient. And this is how you can think of photons later on. Now, an interesting thing that you can do now is you have here you have here a 2x2 matrix, and any 2x2 matrix can be diagonalized. And so in various fields of physics, people diagonalize matrices, and then this has some meaning. So why don't we do that also, and then we'll figure out afterwards what the meaning of this is. Yeah. So that's well, as you will see, this will lead to laser-driven dissociation or laser-dressed states. Yes, so I give this one, I mark this one, and now we'll say like we want to diagonalize this one here. Yeah, so you calculate, in order to do this, you have to solve the eigenwert problem. So you write the determinant of E1 minus lambda, E times D, E times d, E2 minus lambda. Yeah, and the result of this is lambda 1, 2 equals E1 plus E2 over 2 plus minus E1, that's now a minus, minus E2 half squared plus E times d squared. Okay, we don't like this one, so we make a second order Taylor approximation. And that is then lambda 1, which I call now E1 prime. And because it's still an energy, so this is E times d squared divided by E2 minus E1. And we have another one, E2 prime, that's E2 plus E times d, E2 minus, no, sorry, these are, of course, the energies, not the field, E2 minus E1. Yeah, so what just yeah, a bit superficially perhaps we can say that our laser field now, yeah, there's a square missing, of course. Yeah, so our laser field leads to so this so these are now the eigenvalues of the field dependent Hamiltonian. Yeah, so these are essentially the eigenvalues now of our laser dressed system. So if you consider the molecule plus the laser field as one system, now these are the eigenvalues. So our nuclei will now no longer move on these field-free states, but on those states, and this shows that the laser has an influence on the motion of the nuclei. And so when we plot this here, what you get is essentially, for low field strength, we have the regular shape of the curves, which looked something like this. And then they go towards the same value. And now we have, so the higher state gets a bit higher, is a bit increased. The lower state is a bit decreased. Yeah, so this, and it somehow scales with, I should add that the dipole here can be approximated as E times R over 2. Yeah, for large internuclear distances, this makes sense because if you for large internuclear distances, the nucleus, the charge, the electron has to localize on one of these two atoms. And the internuclear distance is r, and that means the dipole is actually r over 2. Yeah? The length that goes into the dipole. Okay, so this is an approximation for the dipole. So this goes roughly with E times r squared. Yeah, so it somehow increases like this. Yeah, this is now the field dressed state. And most importantly, there is now the gap here. Yeah, there's a gap between these two states that will open up. And if I go to higher, to stronger fields, this one now looks something like this, and perhaps like that. And so this gap here in between the states open up as we go to higher field strength. Yeah, so even if the field is not resonant anywhere, yeah, so previously we discussed that we can drive here population with a fitting photon, but even if there's no photon energy fitting simply from the field strength, yeah, so what we're actually considering here is no oscillatory field at all at the moment. Yeah, so if we just assume a static field, this would distort the potentials like this and open a gap. And then now let's go back to these vibrational levels that we considered. The stronger the field, the more vibrational levels can escape from the molecule. And that's something that we observe in our experiments. So what's missing here is, so again, this is the field, essentially assuming a constant field. Now, so what's missing is the oscillatory time dependence of the field. And for that, I don't have the time to go into detail, but I'd like to show you a few experimental results to give you, well, sort of an idea what happens then. So first, let's look at this one. So this is now the potential energy curves, not for H2+, but for IBR. Yeah, so the iodine is, of course, iodine is a very heavy atom, and so is bromine, and so the nuclei dynamics here are really slow. And now, in a way, you can think of the field now oscillating so fast that the nuclei don't even care about this, but they feel the average of what's happening to these states. And what they showed in this experiment was when they bring up the molecule to this lower state here, which would usually go into, well, I guess. So they have two crossing states here, and so usually this would produce an excited bromine atom here. So this would dissociate into iodine plus an excited bromine, and this crosses a state which leads to a non-excited bromine. And now by applying a control field at the time when after the molecule was brought up to this state, and then it takes some time to go to this crossing point, and when they apply a control field right at the time when the molecule is at that particular internuclear distance where these two states cross, then they can control the ratio of these two, of the dissociation here. And they can control whether the molecule dissociates in this state or in that state. Yeah, so you see this here by the signal here decreasing at that time delay and increasing there. And you see here there's a small difference of maybe 50 femtoseconds or so, which corresponds to the time that it takes them to get there. And so this is a simple example of how lasers can be used to control simple chemical reactions. Okay, then now let's return to our favorite molecule H2. And here, this shows a similar experiment was done here for H2, but basically using just a single laser pulse. Yeah, so you would ionize from neutral H2 to H2+, and then the same laser, because the nuclei are so light in H2, it takes the molecule just a few femtoseconds or 10 femtoseconds or so to go to this point here. And at that time, the laser pulse is still on. And so the same laser pulse can now lead to a coupling between these two states and lead to dissociation. And what they observed in this experiment was that the energy distribution of this proton was actually structured. So it's a bit reminiscent of ATI, where you have electrons with a photon energy, electron energy peak spaced by a photon energy, and here it's the molecule or the molecular fragment that carries the energy. It's actually here half a photon energy, and the reason for that is that the neutral fragment that's produced here as well. So you have the proton and the neutral fragment. The neutral fragment has essentially the same mass, so it carries the same energy. And so this suggests that somehow the molecule can actually absorb multiple photons after the electron has already gone and ionization is over. And now how can we understand this? Well, one way is you can think of you can not only absorb one photon, but maybe also 2 and 3 to go to this higher state. And then once you're at this higher state, the molecule follows this potential and thereby gains energy. And the smaller the internuclear distance where you go to this excited state, the higher the final energy. But a nicer picture is actually the so-called Floquet picture, and this brings together this field rest picture that we discussed before with the oscillatory character of the field. And then you have here several crossing points, and at each crossing point a gap can open up, and then the molecule can follow this path down, and this leads then to these higher energies. Okay. And a next step now, which also leads us to this to the discussion about rotational dynamics of molecules, is to look into the angular dependence. So this is of the dissociation process. That's already shown here a bit, and you have. So this shows it's basically a polar plot of the dissociation probability or of the proton yield as a function of angle. So they vary the angle between the detector and their laser polarization, and then so they can detect molecules that are aligned perpendicular to the field. And then this essentially drops to 0. And as you go here to these higher orders, actually the distribution becomes a bit narrower, indicating a higher nonlinearity. Okay, and now we will actually look at these plots here. Yeah, so you remember that the gap width here essentially scales with the electric field times the dipole. The dipole is of course along the field, and the times is here a scalar product, so it depends on the angle relative to the field. Yeah? So here the coupling is strongest, and the gap will be wide open. And in that case, dipole and field are perpendicular, so there's actually no interaction, and the field-free states should remain. And when you plot this as a function of angle, what you get is shown here. Yeah? So we have here wide open along the laser field polarization. That would be here at angle 1 or 1 pi. And then perpendicular to it, it's the original value. And the proton momentum distribution that is measured in such a case actually kind of resembles this shape. Yeah, so you have the largest amount of protons along this axis and no protons perpendicular to it. Now, if I can make a change of perspective, yes. So instead of having this crossing point here at the edges, I put it in the center. And now the question that one can ask, actually this resembles a feature that's known from polyatomic molecules, namely conical intersections, where two electronic states cross in a single point, and these have a large importance for many molecular dynamics. For example, the photostability of DNA with respect to UV irradiation. And so in that picture, this appears in diatomics. So the question arose, yeah. So can we use these diatomics to extract some general information about molecular dynamics around such conical intersections? And indeed, one observes, for example, a scattering around this point here. Yeah? So you can think of the molecule that associates as being a wave packet that is then scattered around this point, and this leads, for example, to interference. Whether this is now related to real conical intersections, I don't want to comment on this. Okay. But one thing that we did a couple of years ago was to take this to the next level by using a combination of two laser fields. Yeah, and then this relatively simple picture here on the left can be complicated, it turns into a lot more complicated picture, where you now have multiple states that you need to consider. And you have not only one such crossing points, but as you see in this case, actually four or even 5 such crossing points. Yeah? And from this perspective, it's not so surprising that now the momentum distribution of the protons that we measure is also strongly structured. And however, yeah, so when we observed this, this came as a big surprise to us, because all these momentum distributions that we observed so far always looked something like this. Yeah, sometimes a bit narrower, sometimes a bit wider, but they used to have this almost circular shape, and then a smooth distribution of the count rate along the angle. But then we observed this strongly structured distribution here, and then after long discussions finally found the explanation in terms of these light rest potentials. Okay.
Can you go back?
Yes, please.
There's a whole plane interacting, the red one and the yellow one.
Yeah, so the yellow one is actually there's a copy of this one. Yeah, so it has the same shape, but it lies at a different at a different energy. Yeah, so this is analogous to these multi-photon transitions that they observed here in this very early paper. Only that in our case, the shape of the potential is not so smooth, but it's very structured. And one of the things you can do now is actually to even vary the shape here by varying the shape of the laser field. And you can do this by phase control. So a bit similar to what you're doing with the two color fields. So
Is that in this picture corresponds to the blue, not the blue area, the sea area, the sea color area around?
You mean this here?
This one, yeah.
Well, you should you can try to associate the features here, yeah, these local maxima with the openings of these or the transition points here, yeah. But not really the energy is the energy is somewhat related to the depth, but this is more complicated. Okay, well, time has progressed, but I'd like to still lose a few words about rotational dynamics. Yeah, so we see here that the molecule can have different alignments with respect to the field. Yeah, so actually here we have two fields, and this is why we have a maximum here and a maximum at this axis, but also these intermediate things. And they come not only from the modulation of the ionization or dissociation probability, but also from the fact that we're really steering the rotation of the molecule. And there's a large subfield in strong field physics that attempts to control the rotation of molecules without ionizing them. And well, a couple of years ago, this group from Hamburg, I think they won the competition, if you ask me, because they really showed that you can do this almost perfectly. And so what they do here is they use OCS molecules. So OCS, that's an oxygen atom, then a carbon atom, and then a sulfur atom. So it's a bit like CO2, but one of them is sulfur instead of oxygen. And then they use a sequence of laser pulses that interact with the laser field, with the molecule. And they do this by introducing, again, a dipole. Yeah, by inducing a dipole in the molecule, and then you get an interaction term. You get a torque that acts on the molecule, which is the induced dipole crossed with the electric field. And this is a torque. And this torque can then be used to align molecules. And by having a specialized setup and a tailored sequence of laser pulses, then a third one to actually explode the molecule and detect the fragments, which allows them to extract the alignment of the molecule at a certain time. They created the following molecular movie. And so now my laptop froze. That's stupid. Great. Okay, well, I think for the online viewers, you can actually enter this here, and you can download the movie from the Nature Communication website. And for the others, I will restart my computer, and then we can watch this. And maybe we close the session now. So.